Alright, so we're going to go over the quiz that just happened. So we have the 8 a.m. section and the 11 a.m. section. So this was the quiz 4A for the 8 a.m. section. Now, we're given the question is design a spring that stretches between 0 and 2000 newtons. So we're given F equals 2000 newtons, a range of 100 millimeters, so that means our delta is 100 millimeters, and a casing of 18 millimeter diameter, so our DO needs to be less than 18 meters, our outer diameter. Our G is given as 85 kilonewton per millimeter squared. And the approximate number is n equals 30. So we're given all this information and we have to work out the design spring. So we need D, capital D, and N. We also need to work out the maximum shear. So the way we do this is we have our F equals Kx, F equals K del X. And we know that K from the formula sheet that was given to us is K equals dg over 8c cubed n. Right? So we want to work out what we need to get. So the way we approach this problem is we need to get c cubed over d. Right? So if we write the formula F equals Kx, so dg over 8c cubed n times delta x, where delta x is equal to, this is the same thing. Okay? So if we were to equate them, we will get that if we were to manipulate this data, this expression, we will get equation, sorry, c cubed over d equals g del x over 8fn. Now, notice that when we use n, this is actually our approximate number. So this is also on the slide. This n is actually referring to our NA. So this is actually our NA. This is for just reference that we will use later on when we work out this capital N, which is NT here. Now, so we just put in this in the calculator. So we have 85 times 10 cubed times by our deflection, which is 100 millimeters all over 8. Our force is 2000, and our number of turns are 30. So what we will get is we will get 85 over 8. So let's do the bottom one first then. 2000 times 30. And the top part we have multiplied by 1000 multiplied by 100, and we get 45 over 24, which is 17.708. So 17.708. Now you can assume many diameters here. You can assume many diameters, but this is a small number, so we're probably going to go with, let's say 3, right? Let's say 3. So let's assume. So we're going to assume D equals 3 millimeters. Now, what will this mean? This will mean that our C cubed over D will be equal to now 17.708 multiplied by D, which is equal to 17.708 multiplied by 3, which gives us, so times by 3, 53.125. So 53.125. Now we cube root this, so we get 53.125, and we will cube root this, so cube root the answer, and you get 3.759. Okay. Now we can work out what capital D is, because we know C equals, the spring index is D over D. So our capital D will be equal to C multiplied by D. So that will be 3.759 multiplied by our D, which is 3. So all we have to do is, I'm going to store this, store A, because we're going to use this later on, or maybe not. We'll find out. So times by 3, we get 11.278. So 11.278 millimeters. Now we need to work out our D outer, which is equal to capital D plus D, small d. That will be 11.28 millimeters plus our 3 millimeters, which will give us 14.28 millimeters, which is less than 18 millimeters. Okay. Now, we need to, when we have our answers, we have to, what do we need to do? We need to either underline them or make it a bit nicer. So we can write our D equals 3.00 millimeters, and our capital D will be 11.28 millimeters. So we have our D and capital D. Now we need to work out our N. Or before that, we will do the tau max, and then we will do the N. So how do we calculate the maximum shear? So let's go back. So we know that the formula for tau max is given to us as 8F over pi d squared C plus a half. Right? This was given to us in the formula sheet. Now all we have to do is just sub in these values. So 8 times by 2000 over pi, and this is our D that we have chosen. So in this case will be 3. So there is no correct answer in this. You could have gone for 3.1, you could have gone lower, 2.9, 2.5, x, y, z. But for this case, I just chose 3. You can choose any other value that works. So C we said is our 3.759 plus a half, right? So let's check what this will be equal to. So I obviously saved my number as A, as my C. So that's what I'm going to use. So 8 multiplied by 2000 over pi times by 3 to the power 2. And we're going to multiply that by my A. So alpha A plus 0.5. 0.5. So we get 2410.23 megapascal. Now notice the units, it is in megapascal. So we have our shear as well now. Now we need to work out our N. Now if you look, we were given this. This is approximately what we were given in the picture. Now you'll notice this is a closed squared end, right? And the way we calculate this is, I believe, it's n plus 2, right? So squared and ground ends. So the way we do this is, this was also given in the formula sheet, but still we should know. So this is NA equals NT minus 2. Now we were given NA as approximate, which was 30, 30. So our NT will just be NA plus 2. So that will be 30 plus 2, which is 32. So our N that we have to show is 32. So these are our 4 answers. N equals 32. And for my diameter of 3, I get this shear, and I get this capital D. All right, so this was the first section quiz. So now we have our second section quiz. So this was quiz 4B, the 11 a.m. section. Now we will follow the same process. So we were going to do the exact same thing that we did earlier. So we did. So what's given to us? We're given F equals 2,500 newtons. The range, or del X, is given to you 120 millimeters. And the outer has to be less than 30. Then G has to be 90 times 10 to the power 3. And the approximate term, or N, is 32. Okay. So again, we have F equals K del X. And we know that K is equal to dG all over 8c cubed n, and then times by del X. We have to make c cubed over 3 the subject, so that will be equal to g del x all over 8fn. So we substitute our values, so we have, in this case, we have 90 times 10 to the power of 3 multiplied by 120 all over 8, and the force is 2,500, and our n is 32. Okay, so now if I just scroll back up again, so I just change these values, so this will be 32 now, this will be 2,500, and instead of having 100, I'm going to have 120, and instead of having 85, I'm going to have 90. So this gives me 16.875. So 16.875. So we can assume any d. I went with d equals, let's say, 5 millimeters. So we're assuming d equals 5, so what will happen? That c cubed will be our 16.875 d, which is 16.875 multiplied by 5. So this will give me, so times by 5, 84.375, so 84.375. And all I have to do is cube root it. So my c would be cube root 84.375. So cube root this answer, shift answer. I get 4.386. Now again, I'm going to store this because it's easier for me. I've stored this as A. Now, I have my C, and we also remember that C is equal to capital D over small d. So my capital D will be CD, which is 4.386 multiplied by 5. So we just multiply this by 5, and we get 21.93. 21.93 millimeters. Now I need to check if this is less than 30, so DO capital D plus small d, so 21.93 plus 5 gives me 26.93 millimeters, which is less than 30, so you're fine. So again, let's just box our answers. So D equals 5.00 millimeters, capital D equals 21.93 millimeters, and this is what I have for D and capital D. Now we're not done here. We still need to work out tau max and our n as well. So our tau max will be, it's 8f over pi d squared and c plus a half. So again, that will just be 8 times f, which in our case is 2,500, right? Over pi, and our d, small d, is 5 squared, and our c is 4.386 plus a half. So let's check what this gives us. So I've already done this calculation earlier, so instead of this, we're going to have A is the same still, so 5 and 2,500. And I get 1244.22 MPa. So I'm just going to write over here tau max equals 1244.22 megapascals. So I have my megapascals. Now, similarly, we were given a very similar spring diagram here again. These are squared ends. So instead of having 32, so what we'll do is we'll do NA equals NT minus 2. So 32 equals NT minus 2. So NT equals 34. So our capital N here is equal to 34. So these are our answers if we choose D equals 5. Obviously, you will get different answers for capital D and tau, but you should get the same answer for N. Now let's go on to quiz 3, which is our spring, our threading quiz. So we were given for, this is for 3A. This is the 8 a.m. section, quiz 3A. So you guys were given this is the same problem as 8.81 in the textbook of Shigley. You can check it out there, 11th edition and SI units. You can check that out. But he modified the question and he changed the question. So in the book, it's R equals 5 and R equals 254. In this case, we have 127 and 254, and that's for a good reason, because if you look at without the SI units, they also use R equals 5 and 10. And when you divide them, you get 2. If you divide this by 127, you also get 2. So it's probably for his convenience. Okay. So let's check what we're given for all these things. So we're given power. So this is power at 600 revolution per minute, so 600 RPM. And we're given that there are 8 bolts here. So there are 4 on the radius of 127, and there's a 4 on the radius of 254. Calculate the minimum nominal diameter of a bolt if all bolts are supposed to have the same diameter and not exceed a shear stress of 138 megapascals. So initially we're given P equals T omega, and we have to work out torque, because you'll see later that this helps us later on when we need to calculate anything, because we can't calculate anything else if we don't have the torque, right? So torque is torque, if we were waiting for torque, P over omega. Now we have P, but we don't have omega. Omega is 2 pi n over 60. So 2 pi times n, which is 600, over 60. So let's check. So let's do 2 pi. So over 60 over 2 pi times 600. And we get 62.83 rad per second. So 62.83 rad per second. Now I'm just going to shift store this maybe at D. So this is my D. Okay. So power is 186.42 kilowatts. So times 10 to the power of 3 over 62.83 rad. So this will give me a torque of, so all I have to do is just do 186.42 times 10 to the power of 3 all over my D. This will give me 2966.97 newtons. Okay, so this is my torque. Now I have the torque, and I have to work out the minimal nominal diameter of the bolts if all bolts are to have the same diameter. Now, so the way we do this is we need to work out, there are different forces acting on F. This force at these bolts that are a bit more closer to the center, and there's another force F at this. So first, let's define these things. So we have R1, or let's say D1, is equal to 127 millimeters. So this will give us R1 of, so what's 127 divided by 2? 127 divided by 2, 63.5. So we got 63.5 millimeters. And our D2 is equal to 254. And if we divide it by 2, we get, so 254 over 127. So our R2 is 127 millimeters. Okay, so we also know that we have 8 bolts, so we have 4 bolts, we have 4 of these, and we have 4 of these. Now our torque should be, this torque should be equal to all of the torques combined. Now all of the torques combined would be, so T should equal 4 torques of the 4 bolts, so 4 bolts at R1 plus another 4 bolts at R2. So we know the T equals FR, so 4 F1, we can call it F1, right? R1 plus 4 F2 R2. Now, we also know this is 2966.97, right? equals 4F1 multiplied by R1 is 63.5 plus 4F2, and this is 127. Now we need a relationship between F1 and F2, and the relationship is that F1 over R1 will give you F2 over R2. Now once we know this, we can work out what F2 is in terms of F1, right? So this would give you F2, R2 over R1 multiplied by F2, sorry, F1. So our F2 will be, so what's our radius for second one was 127 divided by 63.5 times by F1. So F2 should be, let's check 127, answer, or 127 over 63.5, and that's 2. So we know that F2 is equal to 2F1. So 2966.97 equals 4F1 3.5 plus 4 times 2F1 127. So let's add this in the calculator. So let's do 4 times 63.5 plus 4 times 2 times 127. This gives us 1270. So 2966.97 gives you 1270 F1. So F1 will be 2966.97 divided by 1270. So this will be at, so 2, what do we have over, yeah, so this answer divided by 1270, and we get 2.336 2.336 kilonewtons. So we have our F1. Now F2 will just be times by 2. So F2 will give us, so we just times this by 2. So times by 2. Or rather, actually, let me just store this variable as B, and then let's times it by 2. So, and I'll store this as C. So 4.67. 4.672 kilonewtons. We have F1 and F2. Now, we also know that a shear stress is given is 138 megapascals. Now, in this shear stress, we have that it's shear stress T max. Now our allowable stress is 138 megapascals. Now we know that stress is what? Stress is force over the area. Now, we can't work out D unless we go here, and we have to use these tables. We have to work out the area that we can find, then we can go on this table that was provided to us and see where it comes. So area that we should get is force over tau max. Now the force we have is, the maximum force is 4.672 times 10 to the power of 3 over 138 megapascals. So 4.672 times 10 to the power of 3 over 138. This gives us 33.8. The 33.8 millimeters, or if you round it, 3.9 actually, 3 millimeters squared. So our area that we have to use to look at the graph is this. This is the stress area. Now, if we were to zoom in a bit, you'll find out that you'll see that 33 is around, okay. So we have the stress areas over here. So we find out that this is 28, and this corresponds to M7. And then we have 36. Now our stress area is larger than 28.9. So we know that our diameter should be M8. So this is the next allowable diameter that works for us. So the minimal nominal diameter will be 8, so D equals 8 millimeters, so M8, that's your answer. Okay? So that is for quiz 3A. Now let's go on to quiz 3B. So we have quiz 3B. We're presented with a figure, so this is the figure that we were presented with, and this also said 1.5. So the distance between the end and this has to be 1.5d. Okay. So the figure shows a pressure vessel with a gasketed end plate, and the internal pressure is sufficiently uniform, and that the bulk loading can be considered static, and we're told that it's at least 30 megapascal. So this is 30 megapascal that's acting on this internal vessel. So we're also told that 60 millimeter and 20 millimeter bolts are to be used. So we're going to look at M16 and we're going to look at M20 from the tables. And determine the number of bolts needed. Which size is more convenient? So we have the following quantities. Let's look at if we can understand what's going on. So if I was to label D as my diameter of the cylinder, so if I write diameter of the cylinder, and then if I have the P as my pressure in the cylinder, so pressure in the cylinder, and if I had the core diameter, which is DC, or minimum nominal diameter, so that would be this diameter here, this D here. So let's call that small d, right? So D is just the diameter of the bolt. So this is the bolt. Okay. So after that, we also have, we're trying to work out N. We're trying to work out the number of bolts. So N is the number of bolts. Number of bolts. And then at the end, we have to look at which size is more convenient, and we will do that in a bit. Okay. We're also told that the space between two consecutive bolts is 5d, and there's a space, and it has to be less than 10d. Okay. And the maximum allowable stress was also given, which is 200 MPa. So our maximum allowable stress, so let's write, maximum allowable stress is also at megapask. So this is given to us as well. So did not write that down. So this is also given to us. Okay. So the way we do this is we need to work out the force, upward force acting on the cylinder cover. Now, how we do this is our force acting on the cylinder will just be pi over 4, which is our d squared times our pressure. Now, how does this make sense? I'll explain. So this is pressure equal to what? Force over area. Force is equal to pressure times area. So our pressure is 13 megapascals times by pi over 4 d squared. D is a capital D squared. Now, what would this be? This force here would be 13 times pi over 4 d squared. Now, d we said is what? Our d is over here. This is the diameter of the cylinder. So if you look here, this is the diameter of the cylinder. So our capital D we can write over here is, so let's label something. So D equals 140 millimeters. Pressure in the cylinder is 13 megapascals, right? What else do we know? We also know that the nominal diameter is what? The nominal diameter, or rather the small d, d1, is also given. Is we have to work out, we're working with 16 mm or 20 mm. Okay. Anything else that's given? We're given the DO, right? We're given the whole, so this over here is DO. What else are we given? We're given 230, so this is our DP, right? And that's about it, okay? So, how do we continue the question? So what we do is, we know that this force that we generate, right, let's put in the values now. So F equals 13 times pi over 4 Capital D is, which is 140, we discussed this, so 140 squared. This force is resisted by n number of bolts. So this force here, if I call this this force here, is resisted by n bolts. Okay. How do we know this? Is because we want to work out the amount of bolts. So if we were to just look at this, so this force, let's call this F1. F1 is resisted by the number of bolts by the force allowed by the bolts, right? So F bolts. Okay. Now, how do we do this? We have to work out two things. First, we'll do F1, and then we'll do F bolts separately. So F bolts, we have to work out for both the M16 and for M20, right? How do we do this? Is same thing, where we know that the max stress, so I'll do this separately first. Let's do this one first. So we're given 13, so let's put it in the calculator, 13 times pi over 4 times by 140 squared. So we get this one. So we get 200, so 200, 119.452 newtons. And this equals either M16 F bolts or M20. Let's look at M16 first. How do I work out these force given by each bolt? So the way we do this is, so FB will be same pi over, so again, if you remember, P equals F over A. The maximum allowable stress for the bolt is 200 megapascals, right? So 200 times by the area will give you the force. Now this FB will be, for M16, will be pi d squared over 4, right, times 200. Now D represents what? D represents the, small d represents the bolt diameter, which is given to us 60 millimeter or 20 millimeter. Okay. So this will be equal to pi times 16 squared over 4 times 200. So let's check what this will be equal to. So pi, so we are already, so this is now 16 and times by 200. And we get 1280 pi, which is 40212 n. So n in this case should be, let's check. So 200, 119.452 divided by 40212, and that's around 4.97. So 4.97, we go to the next allowable one. So the number of bolts we'll need is 5. So that's for M16. Okay. Now let's try for M20. We do the same thing here. So again, this force here stays the same. What changes is our n and what it's multiplied by. So again, we will do FB for M20. This will be pi d squared over 4 times by 200. This will be pi, and d is 20 here, squared over 4 times 200. And this would give us, so this was 4212 newtons. And this will give us, let's check. So we're going to change this to 20. And that is 62831. 62831.8. Right? So we have this is 62831.8. And all we're doing is answer, and we get 3.18. So n equals 1.18. So n equals 4 for M20. Now another way we could do this is, for example, if we want to just find the answers quickly, if we could just equate the two together. So pi over 2 d squared times the pressure equals pi over 4 our small d squared times by our allowable stress times by n. And we solve for n. Let's try this on our calculators. So we will get, sorry, this is also pi over 4. You'll notice a lot of things cancel out. So if you look here, this cancel out, and you're left with n equals d squared p over small d squared allowable t. So that would be, in this case, capital D, which is our 140 squared times 113 over this 16 or 20 squared times 200. Now let's check if this gives us the same answer. So 140 squared times 13 over 16 squared times 200, and you get 4.97, which we got earlier. And we're going to change this into, and we get 3.18, and yeah, we go to 4. So n equals 4 bolts for M20 and n equals 5 bolts for M16. So now, how do I work out the spacing? Now we have to look at the spacing, right? Okay. So part B, let's add another page. So part B was, so we're given, we know that we have 5 bolts for M16, and we have 4 bolts for M20. Now the spacing that we have to work out is, what are we working with? If you look over here, we're working with only this spacing. We're working with 230 millimeters. Now, you're imagining this as a rectangular vessel. That's not true. This is a cylinder. So this is actually, if you were to look at this, right, this is like this, and it's going inside, and then it's coming out, and it has something like this going on. So this is what's going on over here. So this is our vessel. This is our vessel. It's going on. So this is a cylinder that's going around. This is our casing. So with this, the allowable that we're working with is 230 millimeters from here to here. Now, this is our circumference that we are working with. This is the diameter, right? So if you look here, this is, so if I was to draw it here maybe. So we're working with, so this is our 280 diameters. And then if we go a bit closer, this is what we're working with, okay? These are where the bolts will be slotted in, in this range. So in this range here, in this range, which I'm showing my red dots, this is what we're working with. So this distance here to here is 230. So what are we working with? We're working with circumference. The circumference of this would just be pi d, right? Which is 230 pi. So this is what we're working with. All right, this is what we're working with. Now, we're already told for what? We're already told that we have 5d space and 10d for the other. Now, how many bolts do we have? How many bolts do we have? Let's check. We have 5 bolts for M16. So let's look at M16. If I have 5 bolts, so 230 pi divided by 5, let's check what this gives us. So 230 pi divided by 5. This gives us 144.5 millimeters space per our each bolt. Now, what do? We divide by its d, which in this case is 16, right? To see how much apart is it, what's the multiple of d right now. So we just divide by 16, and we get that it's a 9.03d. So this is within the range. So this is still okay. Now let's try for M20. You have 230 pi divided by 4. So let's go back up again. So divided by 4. This gives us 180.64. So 180.64. And we divide it by our 20 here. So let's check this. Let's divide this by 20. And we get 9.03. So again, if you look here, we also get 9.03. So they're both 9.03 distance apart. So they're both fine, right? Now, they both satisfy the given guidelines, so both are fine to choose. Now, one may say that you can choose. Let's say you want to say something else. For example, you might say that 4 bolts are easier to manufacture than 4 bolts, than 5 bolts, right? You can go with that and say that M20 is better, right? But you can also go up here, and if you compare, look, so we had 4.97, right? And we're at 5, right? And if we had 3.18, we went straight to 4. So this can allow for more stress or anything that can happen to the vessel more than, for example, this stress here, right? So this is just some things that you can compare, because this is more of a understanding type of question here that you have to answer for part B. But they both satisfy the limits that we were given, 5D, space, and 10D. Okay? So that's it for this quiz walkthrough, and I'll see you guys later. Good luck.